Okay, hi everyone. Um, any questions? Anything you want me to talk about? Homework, I don't know, administrative. Can let me know in the chat. All right, so yeah, so today we'll talk about basis. First, we need a result that I have to finish proving. So if you have a vector space V and you have some S so that its span is the whole set, and you know that S, I don't know, suppose it's like some big number M, or I say N here, then if you give me any other linearly independent subset of V, then that set will at most be equal to N. Now, just to note, we might have that span of T is not equal to V, even though span of S is V. In other words, when you have a linearly independent set and you know that its size is strictly less than something we will talk about, the dimension, then you need to add more vectors. So as a concrete example, take S to be 1, 0, 0, and then 1, 0, 1, 0, and then 1, 1, 0. Size of S is 3. Take T to be the independent part, like this. And in fact, let me add one more guy, 0, 0, 1, like this. So in this example, span of S is the whole space. Size is 3, size of T is 2, and then span of T is only contained in R3. Okay, so in order for me to get the full space, I needed to add one more vector. So that's the situation we have. Okay, so you might have independent set, but it's not the full thing. Okay, any questions? Oh, questions. Oh, I see. Let's see. I see. Another result, yeah, for homeworks, let's actually talk about at the end. So I thought it was like administrative, not like math. Another result would be V is the superset of span S. Right, yeah, so it's the, that's right, it contains it, the biggest space possible. All right, let's prove this. So again, you have S and T, and if T was a subset of T, if T was a subset of S, we will be done, right? But that's not necessarily the case. So let me say this. Let me write it in. If that was the case, then T is less or equal than S. So yeah, so we might not have that. So we have to, in a way, put T inside the span of S. So we know W1 is spanned by this guys because this is the whole space V. And we do the following trick. We write W1 in terms of all the V's, and then we isolate one of the vectors. So we know there exists at least one of them whose coefficient will be non-zero. Otherwise, it's not in the span of it, right? So we know that. Then using the field property of inverse, so this is known because AJ is not zero, we invert. So we isolate for VJ, isolate VJ. And now we can ignore it, right? So you give me some arbitrary element X and I remove Vj. I just put W because I have an expression for Vj. So in other words, we showed that span of V1 to Vn can equal the span of V1, Vj minus 1, and then W1, which is one of the elements of T, right? So, right, anyhow. So you repeat this procedure and you get that V is the entire span of yeah, anyhow. So since we assume that K is bigger than N, the size of T, we showed that the first two generate V. Okay, so here's the contradiction. Well, if you do this, it means that you have an extra guy, Wn plus 1, which is in V, and it's also spanned by the other guys. But this is a contradiction, and the contradiction is that we know that the set T was linearly independent. So it means that Wn plus 1 by definition is not in the span of any of the other guys. So that's the contradiction. So indeed, size of T will be less or equal than size of S. Perfect. So let's start our, so if you have a question about this, just let me know. So what's going on here? We have some vector space V, let's say R3, and we want to find some collection of vectors that will give us the entire space. So before we talked about 1, 0, 0, 0, 1, 0, 1, 1, 0, and 0, 0, 1. These guys do span the space, but they're not efficient, but not efficiently. Because this guy here is redundant, this vector, since it can be generated by these two, linear combination. Right, so that means there's a game here. You want to add enough vectors to span the space, but not that many that you have redundant vectors. So there's a perfect choice, and that perfect choice is called the basis. So you have enough vectors to span, like in this example, but not that many that make the set linearly dependent. This set over here is linearly dependent. So S is linearly dependent. Okay, so that's the game we play. All right. Good. And as we will talk about in the next slide, the number of elements in that basis tell you exactly the space of the dimension. So in the previous example, we have 4 elements here, but we know that the dimension of R3 is 3, right? If you put it in coordinate. So clearly there's some extra stuff here, but in the basis, there's nothing extra. All right. So we define the dimension to be the number of elements in any of its bases. So let's do R2 again, just more simply. So we have 1, 0, and 0, 1 is a basis. 1, 0, and 1, 1 is also a basis. What else? Is there anything else? Yeah, you can also play with these numbers. I guess you can have like 1, 1, 0, 1, and so on. So all these guys all have size 2. And that's a general fact for all vector spaces that I will prove in the next slide. So, and it's quite incredible that the size of the space is an invariant for all bases. Okay. Yeah, so we'll prove this next. And once you write your element down, each of these coefficients is called the coordinate. So in other words, x is a1 to an, if you want to write x in v. Okay. That's another notation that we will use next week. Any questions? Can we prove it's the case? Yeah, we'll prove it right now. So given a vector space V, and you give me 2 bases, then we get that they're equal in cardinality. So let's do that. All right. Now, from the result we just had, what did we have? We had this guy was the T guy, and this guy was S, right? We had span of S is V, and T was Li. This was the W1 to WK, and this one was V1 to Vn. And we showed that cardinality of T is less or equal than cardinality of S by doing that replacement. So we get this. We get that the size of B1 is less than the size of B2, but you can play this game the other way. So you can now call this guy T, call this guy S, and so again, you have T is less than S. So you put these two together, and you get that B1 is equal to B2. Right? Is that okay? Okay. Good. So let's do a simple example before we go into our main result. Yeah, so we have this set, and I want to prove it's a basis. So I want to show it's a basis. All right. So, and the space we're looking at is interesting. So we have R3, and this is X, and I put the Y on top. So it's basically this flat plane like this. Let me do it in color. Too many lines. It's like this. Okay, and then these are the axes. So it moves that way. All right, so it's this flat plane, and we claim that these two guys are a basis for it. I mean, this is something you've seen before in other courses. So let's do this. Yeah, we don't have to. I mean, okay, I'll do it slow because your first time. It's been a while. So how do you check that something is a basis? Okay, so that's first we check span. That's what we do here, check span. So how do you do it? You give me some arbitrary element from this space. Okay, so it's arbitrary, and you need to generate it using elements from the field, in this case R. So they're both in R. And we can do that because we have vector addition in the other way. So we decompose the vector into these two guys. So indeed we get that this R2 copy inside R3 can be spanned by these two, right? I think that's okay. All right. And yeah. And also you can play this game in reverse. So you give me any two elements of span of S. We can, again, do vector addition, but in the right direction in a way. So then you can write them in component form, which you know is a subset of this W space. So we get that span of S is equal to W because we did both directions. So in general, when somebody asks you, show V, I don't know, W is equal to V, the fastest way is to show this first and the other direction, right? That's the usual proof technique. Okay, good.
I have a question.
Yes.
I was wondering if, like in Math 224, we make a specific like distinction between the two different like symbols for subset, like the one where you have subset and then there's like a line underneath, which can sometimes mean like subset or equal to.
Oh, yeah. So that's right. So
Doesn't matter.
yeah. So here I should have written like this. Yeah.
Oh, okay.
Yeah. Thank you.
So
this is new, and then over here, yeah.
okay.
Yeah.
So when we write it without the line, then it's implying that.
Yeah. So for example, W is a strict subset of like this guy here is correct.
Oh, okay, I see.
Yeah.
Thank you.
Yep. And yeah, so now let's do Li, and the way you check independence, you find the 0 element for your vector space, 0v. So we'll do more general examples. I just want to refresh your memory. So you set this to equal to the 0 element of your vector space, like 0 polynomial, 0 matrix, 0 whatever. And you need to get that the coefficients are 0. That's the condition for linear independence. And this one works here because what do you get? You get A1, 0, A2 is equal to 0, 0, 0. And then you compare components. So you have A1 is 0 and A2 is 0. That's all. In this case, it's very simple. Okay. Oh, Mayma says how to write the process for proving. I just did that. That was the proof of that. I went in two directions. Oh no, you changed the vector. I'm sorry. Right. It's the same way, exactly same way. So, so you give me x, y, 0, and yeah, we have to play a little bit. So let me see. So you need 1, 0, 1, and you have, so this will be x, that's okay. But then this guy will need to be y minus x. So when you add them, you get the thing I wrote. Is that okay, Mayma? Yeah, good. All right. Yeah, let's prove our main result for today. And yeah, we have time. So we can prove this and then spend the rest of the time doing examples to give you some practice. All right. let's do this result. So it says the following thing, that if you give me any basis, so like, 101 and 100, yeah, like the one Mayma just mentioned, you can write any element of the R2 copy we talked about uniquely in terms of this guy. So meaning these coefficients are unique. So if you have X, might as well go to the next slide. So if you have two expressions with AI and BI, we claim that we get that A1 is equal to B1 and AN is equal to BN. Okay, so there's uniqueness in the expression, which is very important because we want to have unique coordinates. I mean, in applications, that is a big, it's very important that you have a consistent representation for your data. Yeah, okay. All right, so how does this work? Well, assume you have two expressions, like I wrote here, and then just take their difference, right? So this is a field, and we can add the additive inverse. So add additive inverse of the BI V. All right. Okay, so on both sides, add the additive inverse of BI VI. So on the right hand side, you get the zero element of the vector space because they all cancel out, right? So you have things like B1 minus B1, V1, and these are 0F V1, which we proved last time to be the zero element. So you get this expression of these differences. Okay, and yeah, can someone tell me why from here we get this guy here, that they're all equal? It's one word, two letters. Yeah, Li, thank you. So exactly. So then Li forces the coefficients to all be zero, right? Because this expression, for this expression to be zero, we require the coefficients to be zero. So we get equal for them. Yeah, that's the, because if one of them was not zero, it will mean that you can write one of them in terms of the others, right? Linear dependence. All right. Good. And I think that was it, right? Oh, I see. It's interesting. So I have to do both directions. So I showed that if it's a basis, you have unique expression. Now the converse is, suppose you have a set and you have a unique expression. So let me go here and explain what they say. So you assume that every X in V is a linear combination of the VI. Okay, now we will show that S is Li. So this is not an assumption. This is something we need to prove, because then this plus this imply that S is a basis. That's okay, right? So, right. Okay. So yeah, it suffices to show that S is linearly independent. Suppose otherwise, so you have at least one element, let's say the first one in S, that you can write it in terms of the other ones, right? That's the definition of linear dependence, right? So we do this first. So this is proof by contradiction. But then we also have the following. We know that V1 can equal 1 times V1, right? So we have two expressions. We have 1 times V1 is equal V1, which is also equal to B1 V2 all the way to Bn Vn. So 2 expressions of the same vector. But this is a contradiction. So it's a contradiction to uniqueness. Oops. Because V1 is not equal to V2 Vn. So here we show that you can write it in one way or you can write it in another way. Okay, so that's the, yeah, that's the contradiction. Yeah. Okay. Maybe I should do one more. That's all right. So let's see. We have some examples here. Yep. Oh. So let me do. I wanted to do another proof, which is the one from the book. So I did my proof, but I want to do the same from the book. Right. Yeah. So let me prove this one more way in case, because you're gonna read the book. So let me prove this a different way as well. So, right. So assume S is Li. Then what do you have? You have that A1, that it's linearly dependent. I'm sorry. So it's S is linearly dependent. Then you have A1 to V1 and AN to Vn is the 0 is equal to the 0 of the element of the vector space. So you have that, but we also know that 0f times vi is the 0 element. So this is something we proved last time. Okay, so now you put these two together, you know that 0f v1 all the way to 0f vn is the it's the 0 element. Okay, but now you have two expressions and you have uniqueness. So we have A1 V1, AN Vn is equal to 0f V1, or let me write 0v. Then 0f V1, 0f Vn. And then by uniqueness, you get A1 is 0f and so on. Okay, so that's the proof from your textbook. So just to show you there's many ways. So this is a longer proof. The one I did is much shorter. So you can pick and choose whatever you like. Okay, any questions? All right. Okay. So here I have a bunch of examples. And so I have the polynomials and yeah, so let's go through some of these examples. All right. Here's the first one. So the set S is a basis for the space of polynomials. So these guys were the A0, A1x, all the way to AKXK, where you take AI from the field. And X is fixed, so it's a fixed variable. All right. So let's do this. So first you need to show that it spans the space. So we need to show that span of S is pk of f. Okay, so that's what we have to show. And this is easy because you give me any polynomial px, and yeah, you have this expression here, right? But what does that mean? It means that you wrote down px as a0 v1 or v0 all the way to ak v1 vk. So this is v0, this is v1, and this is vk, right? So we show that any element can be written as this case. So this showed only one direction. So let me do the other one, which is more obvious. So this one showed that pk of f is inside the span of S. But, you know, xi is in pk of f. So we have the converse as well. Span of S is inside pk of f. So they're equal. That's okay, right? All right. Okay, now how do you check linear independence for polynomials? So, and I will also do this for the infinite case. I just want to prepare you a little bit before I do that, because it shows up in the homework too. Okay, so why is it Li? We showed the span, but for bases, we also need linear independence. So assume you have dependence. Now, what does dependence mean? It means that you can write one of the powers, like m, for some m. You can write this power as a linear combination of the other powers, where we skipped the x to the m. All right. Yeah, and so let me remind you how you work with these polynomials. So in general, whenever you have an expression of the form a0, a1x all the way to an xn, and b0, b1x all the way to bk xk, and suppose, I don't know, k is bigger than n. So you take their differences. So you have a0, b0, a1, b1, an, bn, and then minus bn plus 1. Then, like I mentioned last time, we use the fundamental theorem of algebra. So remember that the only zero polynomial, zero polynomial that is the only polynomial that is equal to 0 for all x is the one with 0 coefficients. Because by FTA, Pn of x has only n roots, not uncountably many, only n roots. So anyways, that's the game. Any question? All right. So that showed independence.
Wait, sorry, can you
Yes.
go back to that?
Yeah.
So what you were saying about the fundamental theorem of calculus, is that the fact that, sorry, of algebra, is that the fact that we have like a coefficient greater than n, sorry, power, like a degree greater than n? Is that why we know it's,
Well, like, what's a simple example? Let's see. Like, how shall I say this? So linear dependence, right, says that you have, let me do a smaller number, x squared. Let me take 3. So you will need to have something like this: a0, 1, a1 x, and then a 3x cube. So to have linear dependence for that thing we just wrote, you will need to have this to be true for all x in. So our field here, we take it to be real or complex. So, and then, but then you can rearrange this if you like. So you can write this as a 3rd degree polynomial equaling 0 for all x. So each one of them is a root, right? But the fundamental theorem tells us that there's only n roots. You can have more or less. Does that make sense? You're not.
oh,
Yeah, okay. That it's the here you have like uncountably many. Here it says no, you can only have n. Yeah, so this is like the only, I don't know how to say it. FTA says that if your polynomial is non-zero, like the AN coefficient is not 0, the leading coefficient is not 0, then you have n roots. Is that okay?
yeah, yeah.
So yeah, that was the trick. So you're, oh, can we not use uniqueness on S? Can we? That's the one I'm proving. I'm proving because we don't know if S is a basis. We are proving it's a basis. The uniqueness follows only for basis, right? This result was given that S is a basis, right? I guess you could use this. I don't know. It's, yeah, okay, good. But yeah, if somebody can think of a way to use this the other way, it will be interesting, because this is not really a criterion to prove basis, because it asks so many things. It asks show uniqueness, show span. So it's basically the whole thing, except the independence. All right. Okay. Yeah, before I do that one, let me do the infinite case because it will show up. So I should do it on the, I should do it over here. All right. So let's prove a generalization of this. Take S to be all the guys, so x squared, but then let them go to infinity, okay? So I'm doing this here in class because, yeah, part of it will show up in the homework, so I don't want to spread it too much. Okay, anyhow. So take this subset of all monomials, so xn, and it keeps going. And this is a subset of, if you like, PF or PR, let me write PR, or P infinity R. These are both valid notations. And these are infinite polynomials, okay, possibly infinite. So these are all polynomials of arbitrarily large degree, okay, R to R. All right, so this is our set, and we want to show that S is a basis for PR. Okay, so you cannot use this result in the homework, but you can use the proof that I will do. Okay. Oh, I see a question. I was thinking that if we show uniqueness for X, since it's a polynomial, we can directly show S is a S is not a subspace. Be careful. S is a discrete set. Its span will be a subspace, but okay, I mean, yeah, and okay. All right, so again, I will prove this for you, but you cannot use this result in the homework. You will have to just use my proof or modify it or whatever. Okay, all right. All right, so let me show this fact. First, I have to show span, right? So can someone tell me which direction of span is obvious? So span of S and P of F, which containment is obvious? Can I see somebody say, I don't know how can you, is this one obvious or this one, left or right? Yeah, can someone tell me left, right, which one is obvious? Left.
Left.
Okay, can I see some more people? Oh, right. Oh. Yeah, left. Anybody else? Yeah, so it's the left one because we already have the two things. We already have that xk is in the PF, and PF is a vector space. Okay, so it contains all linear combinations. So it contains the span, which is all linear combinations. Okay, so that's the easy one, right? Maybe the right one is also easy. They're both easy. But this one is sort of immediate. You don't have to do any math for it because you already have containment of each of the elements, and your space is a vector space. All right, so we have that. Let's do the other one. So here, what do? This is a little bit tricky. It's tricky because it's infinite. So how would you do this? Here you need to take, so you take a polynomial in this guy, but it needs to be of arbitrary degree. So it would be P of F, P of X, and it would be some arbitrary n. Okay, so then again, you have A01 and so on. And yeah, we know that each of them is an element of in S. Okay, all right. So I think the span is okay. The linear independence, here's something we haven't talked about. So I have to define it here. So extension of Li for infinite sets. So this is done in your book, but it's not really spelled out. So here S, it's infinite, right? It's this, is this. So does anybody have an idea? Can we not keep on adding? Okay, I knew somebody was going to say that. So yeah, you can definitely do that, yes. So what shall I say? Yeah, okay, but it's okay, fine, let me do it, it's fine, yeah. But the point is you can have arbitrary degree in your set, but yeah, you can yes, you can definitely do it that way, but I don't want people writing infinite series, so that's the thing I wanted to avoid, because P of X, if you write all of them, AKXK, where AK are infinitely many, might not exist. So for example, the polynomial Px equal to 1 over k, xk is infinite. At P1, right? This is called the harmonic series. Is that okay, Parth? Yeah, so you're not actually considering polynomials of infinite degree, but instead of arbitrary degree. Yes, we all got it. And then geometric series is not in the set. Right, so exactly. So we're not allowing infinite things. So we don't, this is not the set of power series. This is the set of arbitrary degree. So, and because I'm afraid of things like the one I wrote, where this guy is not even defined for all X. At P1, it blows up. Well, yeah, like the one I just wrote, right? You don't even have wall poseness. So you will need to add something like that, that there's convergence. This, I mean, this goes beyond our course, but you need the absolute convergence. Then you can add them. You have additive structure. Is that okay? Yeah, exactly. Yes. So you need absolute convergence, and yeah, and same interval. Exactly. Absolutely. Yeah. Yeah. Absolutely. All right. So yeah, I'm happy I'm doing this example because it will show up in your homework and it's very tricky. So arbitrary degree, that was one thing. And then second thing, for extension to Li for infinite sets. So, right. So here S is infinite. So the most you can do is take all possible subsets. Okay, so I'm not allowed, again, I'm not allowed to write this A01, ANXN, equal to 0. I'm not allowed to do this because we don't have power series. Okay, so this is not allowed. What I am allowed to do is take all possible subsets. So we take I1, x to the I1, all the way to AIK, x to the IK equal to 0 for some IM infinite. So IM starting from 0. Is that okay? Right, I see my time, but I'm done here. So, but from here we can do the same thing. So given any subset like this, apply FTA to get AI1 all the way equal to AIK is the 0 coefficients, because FTA applies to any polynomial, and this is a polynomial of degree IK. So it has at most IK roots, not infinitely many roots. Okay, so that's the trick for the infinite stuff. All right. Okay, so before you go, let me give you a hint because I put it in the reflection quiz. So for the space of continuous functions in C01 to have infinite dimension, there's many ways. I mean, you can play with sines, you can play with cosines. Another one is, anyways, so these are my hints. You can play with various objects, E lambda x, EKX, sine KX. Okay. Anyhow, all right. Thank you so much, guys. Killian says, what is the technical difference in that? Can IK be like N? Yeah, IK can be like N, but the technicality here is, where is it? That we don't know what IK is. Sorry, what, we don't know what I1 is. Like this could be, let me do like a silly example. It could be x squared plus, you know, a4, x to the 4, a 100, x to the 100. So it's not like a nice ordered polynomial, right, Kellyanne? So we took arbitrary elements. Okay. Maria says, what does C01 mean? Yeah, so these are the I talked about it when we talked about vector spaces, I think. But yeah, these guys are, and it's also in your book, I think. Yeah, I remember this. So, and yeah, so these are the functions 0, 1 to R that are continuous. And remember when I talked about this limit stuff? So continuous just meant f of x0 is equal to the limit of f of x as x goes to x0. Is that okay, Maria? Yeah, so that's my hint. Because I want people who attend the class to get it. All right. Yeah, thank you guys. I have a question for the written homework for problem 4, part 3. Do we have to prove or defined? So it's not prove, you have to, how do you say it? I mean, Boris sort of gave it away on Piazza, so I can talk about it. So the axioms, oh, I see. I'm not no, I don't think so. Because like, no, what you have to show, so just to be clear, right? In class, we proved that if you give me any field to some power, in this case 3, it's a vector space, right? So if you give me a subset of it, which is the one with the not stuff, you have to show subspace. So you have to check the closure. Remember, there was a closure criterion. What? What happened? Wait, what? Well, you are, but in a way you're using stuff we've done. It's not like out of your, you don't have to like go too far. You can use stuff we've done in our course. Well, I mean, I don't want to give it all away. So, yeah, I mean, I don't know, like, what should I say here? I'm not sure if there is any other way to do this. Like, you should probably go on Piazza. Boris gave a post about this. So yeah. Right. So you do have a vector space, but then you need to define the subspace, and you need to prove that this guy is indeed a subspace. And we proved in class a criterion called the closure criterion. So the addition and multiplication are inherited from the bigger space. Right? Is that okay, Kellyanne? That the vector, what? No. This is not this. Okay. This is F3 of F3. F3 is the modulo field, and F3 to the n is the tuple. Oh, okay, good. Someone had some more questions about homework. Just feel free to speak up. In the beginning, I saw something. I said we'll talk about it.
Oh, right. Do we need to define like the addition and scalar multiplication for any arbitrary knot diagram, or like I found the post that you mentioned on Piazza, and it says that you can do it for like it says you have to essentially prove it for a fixed knot diagram, but then how do you generalize it?
No,
so
you
that-
should go read what Boris wrote. Boris sort of gave it away. So you should go read that post. Yeah. If you want to, you can still work on it. But yeah, like I said, the addition and multiplication and so on is inherited from the larger space.
Oh, right. So to prove it, could we just refer back to what we did for question 3? Because question 3 was essentially showing like in question 3 we kind of defined addition and scalar multiplication over F3. So could we just refer back to that in question 4 part 3?
I don't know. Anyway, I don't know what to tell you. Like, if it's so much work to, I mean, I'm sure. See, I don't know. You have to see. I can't say that. This is
I
something
see.
you have to figure this out. I mean, let's leave something for you.
Okay. Yeah.
Yeah.
Hi, Professor. I had a quick like earlier when we saw the idea of uniqueness, right?
Right.
So I was wondering if you can like for polynomials, maybe we can kind of like I don't know more easily show the idea that it's truly like when you write something as something a0 and then a1x and accordingly till x to the power of n, right? Since you can kind of easily show it's going to be unique, so can't we use this as a direct criterion to show that 1 and x and all the way to x to the power of n is a basis?
No,
for-
but it's tricky, right? This is a deceiving statement. So it says uniquely,
Mhm.
but it's for every x. So you still have to show span. You know what I mean?
Okay, so so if you take like an arbitrary vector in the
You
vector
need to be
space-
able to write it.
Mhm.
So yeah, this is not a good. I mean, the point of this result is the uniqueness. Like the interesting part is this way,
Mhm.
that if you have a basis, it has a unique. There's unique coordinates. That's the
Mhm.
interesting direction. The other direction is hard because
Mhm.
you need to show span
Mhm.
and you need to show uniqueness. And basis is span plus linear independence. And this uniqueness in a way contains the independence. So you're not really gaining, you know what I mean? Like you're not, if you want to like go the other way, you're not really gaining from here.
I see. Because essentially my basic idea was that you have some polynomial, let's say with the coefficients AI, let's say for like at least the independent, if you cannot write it uniquely, that means there also exists for BI all the way for x to the power of n, right? So, but equating these two polynomials, so same power must have same coefficients. So the only thing possible is when AI is BI. So that kind of gives away the independence
Yeah,
part.
right. Yeah.
And we can obviously say that what do you say, the subset S is a, what do you say, oh, sorry, the set S is a subset of V, because, and V is a vector space essentially, because like, well, like all the things like 1x and all the way till x to the power of n can be written as something of V, right? So it exists in V essentially. So I was, yeah, maybe this is specific for polynomial that I'm trying it out. Yeah, but I see your point. It probably, like for other vector spaces, the uniqueness part will be harder to prove. That's definitely
Well,
true.
even here, I mean, did you really gain? I mean, like even when I proved Li, I did the same thing. I wrote down the coefficients and I said you have equal. You know, it was the sort of same idea.
So essentially, if you just want to show that something is a basis, you just show that it's linearly independent and the span of
Yeah, it's
thing
way
is-
faster because I'll tell you later on we'll do determinants to. So you've done this, right? To use determinants to check linear independence in R.
Okay.
You've done this, right?
I think
before?
we have probably.
Yeah,
I think so.
So we will do the same thing here. We will check Li by in a very quick way by computing the determinant of the coefficients and stuff like that. So yeah, it will be very quick to get Li. Yeah.
And the span part will, like, span of S is V, that will also be, yeah, we just have to show one is the subset of the other. That shouldn't take much time.
Right, exactly. I can't think of yeah, exactly. Yeah. So yeah, I mean the tricky part we did today is this infinite stuff. So is that okay? Like because it's tricky. I didn't type it. I should have, because it will be done on the homework, but I just want to make sure that you guys get it. Like,
so it's, yeah, the basic idea is that it's not actually infinity, but it's like arbitrarily large.
Right. So you're not allowed to take power series. And when you check Li, you need to go through a subsequence, like a sub.
But like, what exactly breaks down if you take something like power series?
Well, I wrote it. Did I write it? So where is it? Like even Will was talking about this. If Will is still here, it was like you cannot add them anymore. Like the one I wrote here, like harmonic series. Remember from calculus, this guy is infinite, and so it's not even well defined. But so the guy here that I wrote, px of k0 to whatever kxk is only finite for x strictly less than 1. So you have and then you can imagine you take some other polynomial qx and you shift it. Now this guy is finite only for x minus 1 less than 1. So you cannot even add them. You cannot add qx and px. Because where one guy is finite, the other guy is infinite. Where the guy, one guy, is like.
Oh my God. Okay. All right. So, and also, something similar might happen when you're adding two infinities, but with like opposite signs, kind of a thing.
Well, okay, you can never add infinities.
Exactly. Yeah, that makes more sense. So essentially, if we involve, like, I think that is similar to the question we had in the written homework, where like R union minus infinity and infinity.
Mhm.
So that is a vector space or not kind of a thing. Yeah.
Yeah.
Mhm.
So this
But yeah,
is-
thank you very much. Yeah, it's two things clarified. Yeah.
Yep.
Okay. So thank you. I'll see you next week. Yeah.
Yep. See.
Hi, Professor.
Oh, hi, Huyun. Yep.
Can I ask a question about the web work?
The web work.
Yeah.
Can you ask it on Piazza? If it's math, I can do it. But if it's like administrative, is it math?
Yeah.
Yeah.
like-
Okay. Yeah. If it's math, let's talk about it.
Okay. So I will show my. I'm not allowed to show my screen.
Like, okay, I can go to the.
Okay. So it's
I mean, okay, you can share. Okay. Yeah. Yeah.
all right.
Actually, can you share? Where is it? Oh yeah. Can you try?
Okay. So for this question.
Yeah.
So I think this question is to like say find several examples of the function. Say for this one, I will find like p prime t equals to a constant like 1 and try this is this function in the subspace of P2.
Sorry, what's the question?
Yeah, so like how to do this kind of question? So is it
Well,
like
yeah, so P2 is a vector space, right?
yeah,
And we proved a criterion, right? What was the subspace criterion?
so it's first to check it's non-empty and then is the addition and scalar multiplication closed under the
Right. So let's do an easy one. So let's do the B you just talked about. So P prime is constant. So so give me two polynomials. P prime is constant and Q prime is constant. Okay. Huyun.
so
So if you add them, what's the what's the addition of P prime plus Q prime?
P prime plus 2 prime. So P prime plus Q prime. Okay, so it's another constant.
Right.
So it's closed under the addition.
And multiplication. C times P prime.
Okay,
C times P. What's the derivative of C times P?
it's a constant.
No, oh yeah, yeah. So it's CP prime, which is C times the constant that you had. So it's C times alpha or whatever,
Yeah.
which is another constant. Yeah.
Okay, so like for the first one, A,
Well, I mean, you should you should work on this. But I mean, is there something that it's weird?
yeah, like it has a P prime and a P, like how to add them together.
Same thing, right? You give me two polynomials, P and Q,
Yeah,
and you know that P satisfies this and Q also satisfies that. And then you have to show that P plus Q also satisfies that, or it doesn't.
so like two example of say in this case, two example of PT, and I will get P prime T from PT, and then and then I check if PT plus QT satisfy this equation.
Or not.
Okay. Okay, got it.
Yeah.
Thank you.
Okay, good. All right, okay, see you guys. I don't see another question.